Here is a data structure that is allowed to lie to you. Ask it whether something is in a set, and sometimes it will answer probably when the truth is no. That sounds like a bug. It is actually a superpower, and it is quietly running inside the databases, browsers, and networks you touch every single day. Picture a database holding billions of records spread across slow disks. Every time someone asks for a key, the worst case is the key isn't even there, and you spent a painful disk read to learn nothing. Do that millions of times an hour, and the thing isn't here becomes one of the most expensive answers your system can give. And this isn't only about databases. Anytime a system can cheaply rule something out before committing to expensive work, that quick, confident no is worth a fortune. Think of a bouncer at an exclusive club, but one with a deliberately foggy memory. He can't recall every face who ever signed the guest list. That would take a phone book. Instead, he keeps a few rough impressions. If your vibe doesn't match any impression at all, he is certain you are never on the list. If it does match, he shrugs and lets you in, fully aware he might occasionally wave through a stranger. That's the whole personality of a Bloom filter in a single image. It can be absolutely certain about who is not on the list, and only ever fuzzy about who is. Hold on to that picture, because every property we're about to meet falls straight out of it. The obvious way to answer is this. In the set is to store the whole set, every key, every string, and check directly. That's accurate, but it's heavy. Hold 100 million items and you're paying for 100 million items. The bouncer's trick is to throw the guest list away entirely and keep only a handful of bits. The whole structure can shrink down by a factor of 10, 20, sometimes more. So here is the actual machine. A long row of bits, all starting at 0. Call its length m. Alongside it, sit a few independent hash functions. Call that count k. A hash function takes any input and deterministically spits out a position somewhere along the row. The same input always lands on the same positions. That's the entire apparatus. A strip of bits and a handful of hashes. The one requirement is that the hash functions be independent and spread their outputs evenly so that different items scatter their bits across the whole row instead of clumping together in one corner. To insert an item, you feed it through all k hash functions. Each one points at a position in the row, and you flip those bits to 1. Insert the word apple and maybe 3 scatter positions light up. You did not store the word apple anywhere. You only left a fingerprint, a few bits switched on, scattered across the row. Add more items, and more bits switch on. Insert mango, insert grape, and the row gradually fills with 1s in a sprinkled, overlapping pattern. Notice something already. Sometimes a new item's hash points at a bit that's already 1. That's fine, you just leave it on. But hold on to that overlap, because it's the seed of everything interesting that follows. Now, the question. To check whether an item is in the set, you hash it again with the same k functions and look at those exact positions. Query apple, you revisit its positions. All of them are 1s, exactly as you left them. So the filter says, probably yes, this might be in the set. Notice the hedge. It says probably, not definitely, and we're about to see why it has to. Try a word you never inserted, say lemon. Its hashes point at 3 positions, and one of them is still 0. And that single 0 is a smoking gun. If lemon had ever been inserted, that bit would have been flipped to 1, guaranteed. It's still 0, so lemon was definitely, absolutely never added. 1 0 anywhere among the positions, and the answer is a hard no. And there's the asymmetry that defines this whole structure. A 0 gives you certainty, definitely not present. All 1s gives you a maybe, probably present. The no is rock solid. The yes carries a small asterisk. One direction never lies, the other occasionally does, and learning to love that lopsided deal is the key to the entire thing. Most data structures treat both answers as equally trustworthy. The Bloom filter deliberately makes one answer certain and the other merely likely, and that single design choice is exactly what buys all the savings. But here's the catch. Query cherry, which you never inserted. Its hashes happen to land on positions that are already 1, switched on earlier by apple, mango, and grape. The filter sees all 1s and reports probably yes. It's wrong. Cherry was never here. This is a false positive. The fingerprints of other items collided to forge a fingerprint that was never actually made. It's the bouncer again, waving through a stranger whose face happens to combine features he remembers from 3 different real members. No malice, no broken logic, just overlap. The more crowded the row gets with ones, the more often some never-seen item lands entirely on already lit bits. False positives aren't a glitch. They're the rent you pay for throwing away the guest list. Now, the iron guarantee, the promise that makes this safe to build on. A Bloom filter can give you a false positive, but it can never ever give you a false negative. If an item really was inserted, all its bits are ones, full stop, so a genuine member can never be reported as absent. When the filter says no, that's the truth. The only lie it can tell is a hopeful yes. And the beautiful part, that error rate is a dial you control. 3 things move it. Give the array more bits relative to how many items you store, and 1 stay sparse, so collisions get rare. Tune the number of hash functions to a sweet spot, because too few and items barely register, too many and you flood the row yourself. The map even hands you the optimal count, roughly m/n, times the natural log of 2. Dial those, and you can pin the false positive rate to about 1% or far lower. There's a genuine sweet spot in the middle. With too few hashes, 2 different items look alike too easily. With too many, every insert paints so much of the row that it fills up and the false positives climb right back. The optimal count sits exactly between those 2 failures. Put numbers on it and it borders on absurd. Spend around 10 bits per item, a little over a single byte, and you can hold the false positive rate near 1%. Compare that to storing the actual keys, which might be dozens or hundreds of bytes each. You're trading a sliver of memory for a 1 in 100 chance of a polite wrong guess, and for most systems that is a wildly good trade. In code, it's almost shockingly small. To insert, loop over your hash functions and set each bit they point to. To check membership, loop over the same positions, and the instant you find a 0, return false, definitely not present. If you make it through all of them without seeing a 0, return true, probably present. No item ever gets stored, no list ever gets scanned. Just set bits and check bits. There's one thing this simple version flatly cannot do: delete. Say you want to remove Apple and reset its bits to 0. The problem is those bits weren't Apple's alone. Mango may have been relying on one of them too. Clear it, and now a query for Mango finds a 0 and reports definitely not, a false negative, the one error we promised could never happen. So removing one item can silently corrupt others. The fix is a small upgrade called a counting Bloom filter. Instead of a single bit per cell, you keep a tiny counter. Inserting bumps the counters up, deleting bumps them down, and a position only truly clears when its count hits 0, meaning no item still needs it. You pay a few extra bits per cell for the privilege, but now you can safely remove items. Same idea, just with the ability to undo. Now watch where this lives. Inside databases like Cassandra, Bigtable, and RocksDB, data sits in stacked files on disk. Before touching the disk for a key, the engine asks a tiny in-memory Bloom filter, is this key even possibly in this file? If the filter says no, and remember, no is always the truth, the engine skips that disk read entirely. Most lookups for missing keys never wake the disk at all. That's the expensive answer from the beginning, now answered for free. Those stacked files are called sorted string tables, and a single read might otherwise have to check several of them in turn. A small Bloom filter guarding each one turns most of those checks into an instant in-memory no, so the disk only ever wakes for a file that might genuinely hold your key. And it's everywhere once you start looking. Content networks use it to dodge the one-hit wonder, refusing to cache a URL until they've actually seen it twice, so they don't waste space on things requested only once. Browsers have used it as a first cheap filter against known malicious links before doing a heavier check. Lightweight crypto wallets use it to ask servers for only the transactions that might be theirs, without revealing exactly which. Even old spell checkers leaned on it to ask, is this string even a word? What ties all of these together is the same bargain. In each case, a Ron yes costs almost nothing, you just do the slower check you would have done anyway, while a confident no saves you something expensive, a disk seek, a network round trip, a heavy lookup. When being occasionally, harmlessly wrong is cheap, and being certainly right is costly, a structure that's allowed to be wrong is exactly what you want. It's a surprisingly deep lesson, one that shows up all over engineering. Sometimes the fastest way to be right is to build something that's allowed to be a little bit wrong, in precisely the direction that can never hurt you. So that's the Bloom filter. A strip of bits and a few hash functions that answer one question with 2 faces, a 0 means definitely not, and all ones means probably yes. It never tells you something is missing when it isn't. It only ever guesses a hopeful yes, and it does all of this in a fraction of the memory of the real set. Definitely no, probably yes. Make peace with that one little lie, and you get a structure small enough to live in memory, yet powerful enough to sit at the front door of half the systems you use.